Okay, so this is some exam feedback for the 2016 Evolution of the Living Earth exam. So just parts B and D. So this is just to give you some idea where you could have improved your answers, where you might have gone a little bit wrong for the 2016 cohort of students. But hopefully also this will become useful for students in the future. You'll be able to use this as a revision aid going over some of the past questions that we have. Right, so I'll just now some just general advice. I will, if you want to flip forward to the actual questions, I'll put some in the put some links in the below general advice here, so you can skip forward to the questions that you're maybe directly interested in. But just some generic advice that's useful for all exams, really. So do expect exams to be a little bit different from years before. So we don't always just repeat questions from one year to another. Yeah, so we are actually asking you to think, to use material that you've learnt during the course and occasionally with outside reading as well to answer the questions. So it's moving a little bit away from the kind of the rote learning and actually getting you to think a little bit in exams. So to help you prepare for this, obviously there are past papers, but I've just mentioned that the questions might not be exactly the same. So a useful thing to do is to look at questions in some of the textbooks, potentially try and make up your own question based on what you think you've learnt in the course. And you could ask maybe a lecturer about your answers to those questions that you found or made up, or post them on the discussion forum on Learn. Okay, so these resources which are available to you, the lecturer and the discussion forum, to help you revise, and you won't get that help unless you ask for it. So going on a little bit more specifics now. So sometimes it's very easy to write a very short answer to a question, and that's okay if there's a little note next to it saying that it is only worth a very small percentage of the overall marks. But quite often it's worth going back, and once you've made sure you've answered all of the questions that you have to, going out, see if there's more that you can add to that question to fully answer it, to add in more details, more caveats, more assumptions perhaps that have gone into your answer. Okay. So that said, you still need to stay relevant. So quite often we find that students make up a question and answer that, or just write everything they know about the topic that the question is about, rather than specifically answering the question. And that's really important that you do specifically answer the question, because if you just write down a bunch of stuff, even if it is correct, if it doesn't answer the question, then you don't get the prizes. Okay. And on that theme, a little bit of a tip down here is that to make sure that you basically it's a comprehension exercise, that you're understanding what questions are asking you. Try looking at some past exam papers and rewriting the question in your own words. Okay, and then going and asking a lecturer, putting it on the discussion board, maybe asking some of your own classmates whether they both have the same meaning, whether they're both asking for the same thing. Okay, so do see if you can check those things out. Okay, so this is one of the reasons why I'm also giving you a heads up. So this is a record of when some of the revision videos or some of the kind of lecture recordings were viewed during the course. So they started uploading videos down here in November, October, the month that's 10, and you can see throughout the course of the course, not very many people were viewing those videos. Okay, so you can see the total number of views of each day is in yellow here, and the total time watched each day is in purple. So you can see on most of the time, fewer than 10 views per day, and this is not 10 people. It could be the same person clicking on the thing 10 times. So with a class of 80, I would expect the number of views to be a lot higher throughout the course. And you can see obviously the exam happened on this day, the 15th of December, yeah, so packing all your revision in towards the end is not very useful. Well, I mean, it's better than not revising at all, I suppose, but it doesn't allow you to go back and ask the lecturer to post things on the discussion forum to check whether your understanding is adequate. So I would recommend that if you are watching this video and you are at this kind of stage in the course over here, that you consider starting your revision a lot earlier than a week or at least 3 days before the exam. And this is the result of that late revision. So this is the total mark distribution of all of the questions in parts B and D. So this is the parts of the exam that I wrote and marked. And you can see here that the mark distribution goes from, some people did very well, got 100%. Some people got very close to 0 or 0. And there's a spread across those. And bear in mind that the pass mark is 40. Okay, so you can see that over half are not doing so well, and most of this is not reading the question, not answering the question, and not getting some of the basics correct. So there's scope here for a lot of improvement through improved revision, hopefully. So we're going to look through the exam now, question by question. So we look through the global environmental change part first, and we'll look at the global biogeochemical cycles later on. So this part had 2 questions. Question 3 and question 4. So we'll just look at question 3 first. So just to give you an idea of what the mark distribution for this question was, once again very broad, but again quite a lot of people missing out on many marks for this question. So I'll just switch back to this here. So what we're going to do here is just look at the question and identify the parts. So although this question doesn't have part A, B, C, D, we're going to try and break it apart and look at what needs to go into the answer. So first of all, it specifies that you have to use some things. Okay, so you have to use a radiative balance equation, possibly 2. You have to use chemical reactions and examples. So there are 3 things that you need to have in your answer. Okay, and the real question is, where's my pointer? How changes in weathering can change global climate. Okay, so we're basically looking for a description of the chemistry of weathering and how that chemistry interacts with climate. Okay. And your answer must include radiative balance, chemical reactions, and examples. Okay. So these are the kind of things that we're kind of looking for. So the chemistry of weathering. If you go back and have a look at some of the lectures on that, but really looking at the interaction between carbon dioxide and water, producing carbonic acid, which can then attack rocks and form kind of soluble products. So this is the equation for the weathering of carbonate rocks, and this is the equation for the weathering of silicate rocks. So an answer here would need the description of both of those because they have different effects on different timescales depending on how much of these products, calcium and bicarbonate ions, make it into the ocean and precipitate out. Okay. So the other important part of this question is the radiative balance. So you could use this equation here. You could have written out maybe drawn the diagram of balance at the top and the bottom of the atmosphere, all those kind of things. But the important thing is to link is that this parameter here, the emissivity, okay, so that is related to carbon dioxide in the atmosphere. So this links together the weathering and the climatic impact. Another important aspect of this question is the time scale over which these happen. So these are very long-term climate changes that govern the long million-year plus kind of evolution of the Earth's climate. So these are the kind of things that you want to go into your answer as well. So examples over on this side. Oh, where are we now? Over on this side. So looking at maybe some of these glacial or long glacial periods, the Carboniferous, the Cretaceous perhaps, and how these were kind of governed, or how the global temperature was affected by changes in weathering rate, and what are the drivers of those changes in weathering. Okay, so this feeds into some of the examples. So things knowing that the temperature, so temperature, amount of water, so temperature and precipitation, so how wet and warm the climate is affects kind of how much weathering goes. So there's a feedback there which you could go in and describe in a little bit of detail. But, or processes such as the physical erosion, physical weathering, increases the chemical weathering rate. So this links in with the plate tectonics and mountain uplift and how that may be responsible for some of these kind of long-term changes in climate here. Okay, So looking at some of the mistakes that quite a lot of people fell into on this kind of question. So obviously not reading the instructions and not including these equations. Not identifying the link between weathering and climate was CO2, and that was specifically change in emissivity. So just writing down the equation is great, but actually explaining how it works and which part of the equation is important for controlling climate and how that links to the chemistry. That's something that was missed out. Some kind of, I guess, somewhat minor sort of semantic. Quite a lot of people say that the greenhouse effect was the atmosphere reflecting radiation. Well, it's not actually reflecting it, it's absorbing it and then re-emitting it back down towards the Earth. And this was quite common, that people didn't really identify that different timescales are important for the relative importance of carbonate and silicate weathering. So silicate weathering draws down 2 carbon dioxides for every mole of silicate rock weathered, and then releases 1 back when that carbonate is precipitated in the ocean, whereas carbonate is a kind of a 1-for-1 weathering to draw down to release of CO2. But on slightly shorter timescales, so kind of less than 1 million years, the weathering and the precipitation in the ocean can be slightly out of balance, which leads to carbonate weathering actually can play a role in climate change, but only on a relatively short term, but short compared to millions of years. And many people didn't write examples, so this was a really easy way of losing marks by missing out part of the question. Okay, so moving on to question 4. So this is split up into 3 parts, A, B, C, with roughly equal kind of weighting between all of the parts there. So, and again, so this was similarly wide range of marks, a little bit lower average than question 3, but again a lot of people missing out on some of the easy stuff here. So the first, give 3 examples of proxies that have been used to produce evidence for quaternary glaciation. So this is an example where people didn't get as many marks as they could by just listing 3 proxies and not explaining them very well at all, just making a list of 3 things, whereas actually what was needed here was 3 examples, but also a little bit of description in terms of what is that a proxy for. Is it for temperature? Is it for ice volume? Is it for precipitation? An example down here, which we could have gone into a little bit more detail to get a little bit of extra marks, was saying, you know, we showed this example in the lectures of the left or right coiling foraminifera being a proxy for sea surface temperature. Okay, so not just temperature, but sea surface temperature. Being more specific, getting more marks, and that is sensitive over this range of temperatures from 4 degrees to maybe 14, 15 degrees, but outside of that it's not a sensitive proxy. So a little bit of extra detail could have bumped you up and got a little bit of extra marks towards the the higher end of the scale. But again, most people were losing marks for not explaining things like, what is it a proxy for? Okay, so what aspect of glaciation, ice volume, temperature, precipitation, what aspect of the climate is it referring to? So again, some common mistakes. Okay, so not using a direct, well, it's basically not mentioning proxies, but using examples which weren't proxies. And the classic one of this was people were saying that CO2 in ice cores was a proxy for CO2. Okay, so it's not, it's a direct measurement. It's a, so a proxy is an indirect measurement of something that can't be measured or isn't being measured. So we could take as an example the magnesium-calcium ratios in forams are a proxy for temperature. Okay, but we can't say that the temperature measured by a thermometer is a proxy of temperature, because it's not a proxy, it's a direct measure. Not stating what the parameter is for, not saying that it's for temperature, or it's for precipitation, or it's for ice volume. Another thing that people wrote down is they said ice cores or deep sea sediments. Those aren't the proxies, those are the things that the proxies are in. Okay, so you need to say what it is being measured in that archive that is the proxy, not just saying the archive itself. And then not linking that parameter. So sometimes temperature obviously would be in glaciations it is colder. Okay, so this is a minor point that would have got maybe a few marks. Okay, so the next part of the question was where quite a lot of people lost a lot of marks through not reading the question. So this is a bit about orbital forcing and why it's responsible for the timing of glaciations, but not the magnitude. Okay, so you can see that this first part of the question is responsible for the timing. Okay, that's not a question. That's just information being provided to you. Okay, so this is saying that the timing, so when these transitions happen, okay, when these things change from glacial to interglacial, that's due to orbital forcing. But it's then saying that the magnitude of the change, so this difference here, that difference in temperature or ice volume or whatever, that is not due to orbital forcing. Okay, so the question is asking you what is responsible for the determining how big these changes are. Okay, so what processes are thought to determine the magnitude of change. Okay, so that's where people got a little bit tripped up because they wrote lots about orbital forcing, but that's not what the question was asking. The question was asking about feedbacks. Okay, so what is it that you have a small initial kind of forcing, maybe caused by orbital forcing, by changes in eccentricity or obliquity or precession, but then that small change is amplified by feedbacks. Now these feedbacks could have been albedo feedbacks, they could have been carbon dioxide feedbacks, they could have been feedbacks to the biosphere, they could be positive, but also negative feedback. So quite a lot of people missed out on mentioning that there must be some negative feedback, otherwise if you only have positive feedbacks the change would carry on and on and on and on and on and on, and we have a runaway deglaciation or runaway glaciation. And we know that's not the case because climate kind of oscillates up and down between these kind of states. So the question was about feedback, so that's where what we were looking for. So again, common mistakes: really not reading the question, really read the question. Writing about orbital forcing because that was not the question, so that was a mistake. Okay. Writing about things that affect climate but not specific to the glacial transitions. So the question was about quaternary glaciations. So quite a few people wrote about things like changing the position of continents, ocean gateways, mountain uplift. These things all do affect climate, but they don't affect climate across these glacial transitions in the quaternary because the timescale is too short for the continents to move around. Okay, so those things were not relevant to that part of that. Okay, and really missing out on the importance of feedbacks. So those were mistakes people made. Yeah. So again, writing about longer timescales than the question was asking for. Okay. And then the last part really followed on from that second part, part B, which was basically to describe the mechanisms of those forcings, or the mechanisms of the feedbacks rather. So two kind of examples of that, if you've mentioned albedo, so this is interglacial state here, glacial state down here. In a glacial state we have more ice cover, more snow cover, it's whiter, have higher albedo, and then it would be a good point here to refer to the radiative balance equation here, and you could have used that to show a change in albedo will lead to a change in surface temperature. Okay, so that would have brought you some extra marks if you could have bring in, without being prompted, some of the equations that you should have learned. Another feedback is the carbon dioxide in water solubility. So if you look at the record of kind of a proxy for a glacial state, which is this in blue here. Okay, so these are oxygen isotopes recorded in deep sea sediments. I think, no, they're probably hydrogen isotopes in an ice core. But doesn't really matter what they are. They kind of show that we go from an interglacial back in time to a glacial and interglacial, glacial. And at the same time as these climate shifts, we can see that there were changes in carbon dioxide. Okay, and some of this change in carbon dioxide is a feedback through temperature based on the solubility of carbon dioxide in water. So when it's colder, more carbon dioxide can dissolve in the water, which means that there's less in the atmosphere, which means that the planet cools. You could refer to the radiative balance equation, this time looking at the emissivity here and how that is responsible for climate change. Okay, so once again, not describing processes, just saying things, like things like temperature, for instance, saying temperature is important. Not leave the process. Not using the examples that you used in part B. I mean, the question specifically said using your answers in part B, so to not do that would have been odd. If you did get part B like totally wrong, I think I did give like some credit in part C for explaining the thing that you got wrong in part B, and if you explained that well in part C, then yeah. Okay, so moving on now to the part D. So this is the Global Biogeochemical Cycles part of the exam. So there are two questions here, 7 and 8. So we'll just again go through those one by one. So this is the first one, question 7. And again, this one was actually answered quite poorly. With lots of people in this case not really getting it. Okay, so just look at them kind of part by part now. So using, again, these are things that need to be in your answer. Balanced chemical equations. Okay, so if you didn't have balanced chemical equations in your answer, you were instantly throwing away marks. Okay, and then we want to show the effect on ocean pH and atmospheric CO2 on the production and decay of organic matter in the ocean. So this question is asking, so if these things happen, if production and decay of organic matter happen, what will happen to atmospheric CO2 and what will happen to ocean pH? Okay, so in this case we start out with some chemical equations that describe, summarize what happens during production and decay of organic matter, and that are kind of these equations for photosynthesis and respiration. So this is a slide from the lecture, and I think in the lecture I did point out that this is not a back, so this is wrong. It's not a backwards and forwards reaction. So photosynthesis and respiration are totally separate processes. They're not the back reaction of another, but photosynthesis takes CO2 and water and produces organic matter, and respiration takes organic matter and produces CO2. So you can see here that if we have production of organic matter, that will remove CO2 from wherever that production is happening, and respiration will give it back. Okay, put CO2 into the environment. Okay, so that's one, basically the starting point, and then what happens to that CO2. Okay, so we could take it in terms of what happens to the atmosphere. So this production is happening, specifically says, in the ocean. So the CO2 is not being added and taken away directly from the atmosphere. It has to get from the ocean into the atmosphere. So you could have gone through and described Henry's law and how there's an equilibrium between the surface ocean and the atmosphere. So CO2 that's removed by photosynthesis will draw carbon dioxide into the from the atmosphere into the ocean. And likewise, if there's respiration, that will raise the CO2 aqueous concentration, which will then lead to an increase in atmospheric CO2. Okay, so that's kind of broadly described. You could have drawn a little diagram, kind of surface ocean, deep ocean, to look at the exports of this production of organic matter, because these production and decay don't actually happen in the same place in the ocean. And then you can go on to talk about pH and how the addition of CO2, so maybe using some of these, actually I think it's in, so these equations down here, CO2 plus water goes to carbonic acid, which then dissociates into hydrogen ions and bicarbonate, and ultimately another hydrogen ion and carbonate. So you could have used those to describe what happens to the pH of the ocean. So adding CO2 from respiration decay would lower the pH. Taking away CO2 through photosynthesis should raise the pH. And then there's a kind of a little bit of a feedback here into the atmosphere. And if you change the pH of the ocean, you change the ability of that ocean to store carbon, dissolved inorganic carbon in the 3 species. So as you lower the pH if you have lots of respiration going and you're lowering the pH of the ocean, you can actually store less CO2 in the ocean. So as well as the CO2 that you're giving out for that respiration, you're also adding more CO2 to the atmosphere because you're changing the pH and you're coming down this kind of this slope here on how much carbon the ocean can store, so that must go into the atmosphere. So again, some common mistakes, really not reading the question. Okay, so this was really quite common. So writing about what happened if atmospheric CO2 increased. So quite a lot of people said anthropogenic CO2 increase will cause carbon dioxide to increase in the ocean, will lower pH. That's not what the question asked. The question asked about production and decay of organic matter in the ocean and how that then affects atmospheric CO2. So quite a lot of your responses were kind of written the wrong way round. Missing out on some of the equations. So when it says use an equation, use an equation. And yeah, so I guess this is an example of where you could have taken your answer a little bit further to get kind of the higher end of the mark scale is to, rather than just think of the ocean as kind of one entity, maybe thinking of it as maybe a layered thing with a surface and the deep, and how the production and decay of organic matter actually happen in different places. Production happens in the surface, then sinks and decays, and that changes the pH and the CO2 content within the ocean. Okay, so it also means that you can store carbon dioxide in the deep ocean away from the atmosphere. So these things which you could have maybe added to would have given you maybe some more marks. Okay, so the next part of the question: what processes in the ocean affects the amount of organic matter, production and decay? So again, the key things here are the word processes. So we're looking for processes, not just parameters, and we're looking for the amount of production and also the amount of decay. So the things, the parameters that control this are the amount of light, lots of light. You can have lots of photosynthesis. The amount of water controls the amount of photosynthesis, but in the ocean that doesn't matter because the ocean is made of water. But on land, that's kind of important. We need CO2 to have photosynthesis, but everywhere in the ocean there's excess CO2. So quite a lot of people said, oh, if the CO2 goes up or down, that'll change the amount of production that can happen. That's not true. There's always excess CO2 in the ocean, so we never run out of it. So it's but what we do run out of is some of the key nutrients. So nutrients like nitrogen, phosphorus. We don't run out of these guys: potassium, calcium, sodium. We might run out of things like iron, which are more scarce in the ocean. But if we run out of the nutrients, then, or if we run out of one of the nutrients, even if we have the other ones there, then we can't have production of organic matter. Okay, so we want to think about what processes limit the availability of those parameters. Okay, so we might think about light. So maybe a process that limits the availability of light might be sea ice formation. Okay, kind of reduces the amount of light getting into the ocean, or it might be kind of the depth of the mixed layer in the ocean. So if you have a very, very deep mixed layer, it might be quite hard for the light to penetrate down to the bottom of it, so you might get less primary productivity. We might want to think about the nutrients in terms of actually what determines how much nutrients we have in the surface. So things like upwelling brings nutrients to the surface, so if we reduce the amount of upwelling, we might reduce the amount of production that's going on. You might also want to think about internal cycling. So if internal cycling is very efficient, we can produce more organic matter. If it's not so efficient, then we can't. So those are the processes rather than just the parameters, which are important. Okay. So this is, so the thing about the upwelling. So thinking about the surface layer and the deep ocean. This deep ocean has got nutrient rich, the surface ocean is nutrient poor. So bringing this water up to the surface can allow more productivity to happen. So I haven't got many slides for decay, but the things that limit the amount of decay can happen are the supply of organic matter. So that's a kind of a process, but also the availability of oxidizers to oxidize that organic matter. So that is mostly oxygen, but if you run out of oxygen, there are other oxidizers available: nitrate, iron, manganese, sulfur. So those are very rarely limiting in the ocean. Oxygen is sometimes limiting in oxygen minimum zones. So mentioning something about that would have been good for limiting the amount of decay that can happen. Because if it's not decayed in the ocean, it will fall into the sediments and be exported out of the marine carbon cycle. Okay, so common mistakes again. So the question asks for processes. If you just listed parameters, then that would not be so good. You still get some credit for that, but processes was what we were looking for. A few people mistook calcium carbonate for organic matter. So calcium carbonate, although it might be produced by an organism, is thought of as inorganic carbon. Oxygen does not normally limit production. So quite a few people said that oxygen limits production, whereas very rarely it does, because production usually happens at the surface of the ocean where there is light available, and the oxygen can exchange with the atmosphere. So you can get oxygen to where the organisms kind of need it. And also most of the production is by photosynthesis, which produces oxygen, doesn't require it. And a quite common was this point about CO2 is not limiting for production of organic matter because it never runs out in the ocean. Okay, so the last question, question 8, was kind of a more calculating type question, or calculating kind of an evil way, in that we're actually asking you to do some kind of calculation. Okay, so this had similar kind of mark distribution. Nobody got kind of like massively high marks on this one, but still quite a few people didn't do so well, and that was mostly because they got the calculation wrong. So I'll go over that in some detail. First part of the question, define residence time. Okay, so it's not worth many marks, 20% of the overall, so what we're really looking for here is kind of a really brief description of what it is and how it's calculated. Okay, so things that should have gone into that, the equation for calculating it, and some kind of description of what it means. Okay, so how long a thing spends in the reservoir on average before it's given out. Okay, so common errors in here is so quite a lot of people use the mass of the reservoir and not the mass of the phosphorus in the reservoir as the mass term. So that was an error. So it's always the amount of stuff, not the total volume or total mass of water in the reservoir. Quite a lot of people omitted the word average from the definition of how long an atom stays in the reservoir. I know it wasn't in the last slide, but I did go over it many times in the lecture. Not providing the equation, easy way of losing marks, because it's kind of a really obvious thing that really should be in there, very easy to do. And then the calculation part. Okay, so what we're really asking you to do is to take that simple equation of residence time, mass of phosphorus divided by the flux into or out of that reservoir, and do a calculation. Okay, so some of the things that are in this, okay, so using the information in the table below, okay, so we provide you all of the information that you're going to need. Calculate the residence time in the surface and the deep ocean. Okay, so we're treating these as separate boxes. Okay, and we'll look a little bit later about what would have happened if we thought about the whole ocean, but this is really looking at those separate boxes. And really key here, lots of marks available for thinking about the assumptions that go into this. Okay, so it might have been a good idea to do a quick sketch. Wouldn't have got many marks for it, but it would have helped you think about what is the right thing to do here. Okay, so we've got all of the fluxes. So we've got the flux from rivers here, and then a removal flux by estuaries. Okay, so actually only a small amount gets inputted from the continents into the surface ocean. Okay, so that's one thing that a few people missed out on. Even if you missed that, you still got through the calculation okay, then you'd have got marks for that. This was a thing. There's an upwelling flux from the deep ocean to the surface ocean, and that's because the concentration in the deep ocean is much higher than it is in the surface ocean. Okay, so it's kind of 50 times, I think, higher. So that means if you mix water up and down between these two boxes, there will be a flux from high concentration to low concentration. Okay, and that's this quite large number here, 900 times 10 to the 12 grams. And then the flux out to sediments from the bottom box. So one thing that wasn't given to you was that actually there must be a return flux down into this box. Okay, because one of the assumptions that we make when calculating resonance times is that the flux in equals the flux out of each of the boxes. So there must be a flux that kind of counteracts this flux here. We'll go on to that in a little bit. And then the other thing which tripped a few people up was actually calculating the amount of phosphorus in each of the boxes. So I gave you the volume of the whole ocean here, and I gave you that this was 100 meters and this was 3,600 meters. Well, I told you that the whole lot was 3,700 meters. I'm pretty sure you can work out the difference. So the mass of water in this box is the total mass divided by this fraction, and then for the deep it's this fraction. And then to work out the amount of phosphorus in that, you need to times that amount of water, okay, by the concentration. Okay, so one assumption I'm making here is that 1 kilo of water is 1 litre. So it has a density of 1 gram per centimetre cubed, which is not true, okay, but it's an assumption which is true to, you know, plus or minus maybe 10%. Maybe plus or minus 3%, 3.5%. So it's quite a good approximation. Okay, so mentioning in its assumption and then saying how good or bad that assumption is would have got you some marks. Okay, so this was also a bit that people missed out on. If you just use the mass of the whole ocean or the mass of one part of the ocean without taking into account the concentrations, you'd end up with the wrong answer. So the next thing to do is to assume this flux in equals flux out. So that's this basically working out this kind of flux to balance our innies and outies. So this is this 902. So actually at this point we could maybe start thinking about, does it matter if it's 902 or 900? Does it matter or not? In terms of, if we look at some of the precisions that our numbers are given to, okay, given to one significant figure here, one significant figure here, does it matter that 900 is 900 actually the same as 902 within the area of the precision of the information we've been given? So not a lot of people thought about writing about that. Some people just use 900. But if you'd have written about that, you'd have got super bonus extra marks. So these are what you have to do with those kind of equations. So if we basically look now, we've got the equation for resonance time up here. Now for the surface ocean, we have the mass of phosphorus in the surface divided by the flux into or out of that box. And then for the deep ocean, we have the same, but with the concentration, or sorry, the amount, of phosphorus in that top box up there. Okay, so you plug those numbers in and you get these answers. Okay, so 21 years and 37,000 or 38,000 years. So I've written down this ridiculous number of significant figures for a reason, because that was another place where quite a few people lost some marks by quoting things to ridiculous degrees of precision, which were inappropriate. So if you look at the precision that some of the data is given to, so 2 significant figures, 1 significant figure, 2 significant figures, it's actually probably best to write this as this is to 1 significant figure, that's 20 years, maybe 21 years to 2 significant figures. This is maybe 40,000 years or 38,000 years, 1 or 2 significant figures. You'd have got credit for using an appropriate amount of significant figures, which is important when you're doing science. So this wasn't part of the question, but let's just think about what we would have done if we were asked to calculate the whole ocean. Because then these fluxes, upwelling and downwelling, they're effectively happening within the one box that we're interested in. Okay, so that's just internal cycling if we're thinking about the whole ocean as our box. So in this case, our flux in and flux out are actually just these fluxes here. Okay, so the resonance time for the whole ocean, okay, is the total concentration or total mass of phosphorus in the whole ocean. So this is the surface, and that's the deep. Just add them together, divided by the flux in or out, and this time it's much, much smaller. And this time we're actually looking at a much, much longer residence time for the whole ocean. So for these smaller subdivisions, we can have a shorter residence time because we can exchange phosphorus between the surface and the deep ocean, and that allows us to change the concentrations of those boxes on shorter timescales. Whereas the whole ocean phosphorus content is very hard to change over because it's got a very, very long residence time. Okay? But we can still have spatial variation because we have this movement of phosphorus between reservoirs. So it's very important to think about what it is you're actually calculating the residence time of. Is it the whole ocean? Is it a layer within the ocean? Is it part of the ocean? Because that will make a difference to what your answer is. Okay, so some common mistakes. Kind of mentioned these already, but using the mass of the ocean and not the mass of phosphorus, that was a very common mistake. Not checking your answer. So some people came up, did some maths, made some mistakes, arithmetic, or used inappropriate assumptions, and they got some ridiculous answers, really ridiculous answers. So residence times of 10 to the minus 16 years, so less than a femtosecond, very, very short amount of time, or times that are longer than the age of the universe. If you do end up with an answer like that and you can't figure out, you just write a note there. Critically assess your answer. Say this is wrong because this is longer than the age of the universe, or this is long because I know that there is variation in the ocean in phosphorus, so this cannot be the answer. If you get the wrong answer and you know you have the wrong answer, say so, and then if you have a nice marker like me, you will get some credit for noticing that you have the wrong answer. Quite a lot of people, inappropriate significant figures, not just putting down lots and lots of significant figures, but quite a few people just wrote 3 significant figures. There's no reason for it to be 3. None of the information was given to you in 3 significant figures, so why would you quote the answer to 3 significant figures? Don't do it. It's wrong. Choosing the wrong flux. So choosing kind of 2 or 21 or 19 rather than the 900 or the 902. Lost some marks, didn't get completely 0 for getting the wrong answer because the whole kind of like a process was being assessed, not just the right or wrong answer. Choosing the wrong flux. And also, there was an opportunity when you chose what flux to use to explain why. So that would have got you a little bit more marks towards the ELE. Also not stating any assumptions. So we've already mentioned that the flux in equal the flux out. The concentrations are not changing, so we're at a steady state situation. And the water density is 1 and is uniform everywhere. So those are reasonable assumptions. Stating assumptions like assuming the information in the table is correct is not a very appropriate assumption, because that's kind of more a philosophical question about truth in general. But if you've been given a number, an assumption that is correct is just given, really. Okay, so the last part of this is looking at the calculated residence times. So using the information that you've got, okay, and actually most people who made mistakes in the calculation, it usually worked out that you still ended up with residence times that were short for the surface ocean and long for the deep ocean, just out by orders of magnitude for both of them. How the variability in deep ocean phosphorate concentration varies relative to the variability of concentration of the surface ocean. So the key things here are the word variability. Okay, so we're not asking about why the concentration is higher here or there. We're asking about the variability in the concentration in the surface ocean and the variability in the concentration in the deep ocean. So we want you to explain this variability using the residence times. Okay, so you can see this is a map of surface concentration of phosphate, and you can see that there's lots of variability in that, and there's allowed to be lots of variability because the residence time is short. So changes in the input or output fluxes, so in regions of upwelling you can have higher concentrations. Whereas if the residence time were very long, if you started adding phosphorus in a region, it wouldn't change the concentration by much because there'd already be lots there. So those are the kind of things you want to use the residence time in your explanation of the variability. Okay. Similarly, if you look in the deep ocean, Okay, concentration profiles do not vary a lot. Okay, and that is because the residence time is longer. You could have gone into a little bit more detail into saying the residence time is approximately the same as the mixing time in the ocean, which makes it almost a conservative element in the deep ocean. But you know, that would have got you the higher levels of marks. Okay, so again, common mistakes: not reading the question, talking about concentrations and not concentration variability. Yeah, like what I just said there. Not referring to the residence times that you gave in the middle part of the question. Yeah, and that's pretty much it. So if I just go to this, so hopefully you'll have some idea of where you might have gone a little bit wrong, where you could have got some more marks if you did okay in some of those questions, and hopefully you can use this for future exams to better attack the questions, to better prepare yourself, particularly using some of those revision tips at the beginning for those exams, and to revise earlier, because that would help you figure out where you need to get some help. Okay, so I hope you found this interesting, useful. Yeah, hopefully we'll be seeing many of you in oceanography and other courses, which are also fun. Yay. Okay, right, so that's me done.